Welcome to part 2 of the Einstein Summation notation lecture. Again, these notes should be posted as links in the YouTube chat channel. If you cannot find them in the doobly-doo below the video, they should be available on Moodle. So let's recap. When we have just a variable written, alpha, beta, lambda, these are just scalars as normal. These are generally constants, or if they're not constants, they are not vectors. And AI, what does AI mean? AI just means the scalar component generally of a vector A, or a vector component. So imagine that you had a vector written as A is equal to alpha, beta, gamma. Then A sub I would be the ith component of that vector. So A sub I would be alpha, beta, or gamma. Never all of them, never the whole vector, right? We often drop this thing here because it's implied that if you have one index, that means vector. If we then have something like Aij, that's then generally a scalar component of a matrix A. So to sort of recap there, if you have just a number written, again, alpha, that's a scalar. If alpha has an index, that means that's a component of a vector. If alpha has two indices, that means that is a component of a matrix. And then we will see here in a few minutes, if alpha has three indices, that is a component of a tensor. Now, what's a tensor? The mathematical answer is technically a tensor is something that transforms like a tensor. I know it's not a very satisfying definition, but we'll explore that a little bit more as the quarter gets going. A tensor is effectively a way of representing something in a vector space, meaning that you have a lot of rules on how to transform it into another vector space, either at higher dimensions or lower dimensions. That's a really rough definition, but without getting into more of the complexity, I don't want to ramble too much about it. But if you want to think about it sort of an SAT way, all of these things are tensors, okay? Or at least example of tensors. What we say is that alpha is a tensor of rank 0, this is a tensor of rank 1, tensor of rank 2, tensor of rank 3. That just means how many indices does it have, okay? So what we can say is that all matrices are tensors, but not all tensors are matrices. Hopefully that helps a little bit. We also have another classification of things that we can do, at least in terms of matrices, and that is we can take their transpose. Then transpose replaces the row and the column definition. So the Aij transpose is Aji, so the transpose swaps the order of those two things. And there's a definition that hopefully you learned in some kind of linear algebra course before now, but if you haven't, you need to understand what antisymmetric means. Antisymmetric is always antisymmetric in terms of the indices I and j. So that means that if you swap I and j, as we've done here, you introduce a negative sign out front. So antisymmetric implies if you swap I and j, you get a negative answer. So normally in a 3x3 matrix, you would have 9 numbers that were all independent of one another. However, once you say it's an antisymmetric matrix, you actually greatly limit the amount of freedom that you have to put numbers in it. Why is that? Well, if you think about it, B11 has to also be negative B11 because you could swap those two. And we do have a number that does that. That number is 0 and only 0. So B could be written as the following. 0 along the diagonal, because we require that negative sign upon swapping. And then if you transpose, that's when these elements end up swapping with one another. And those elements swap, you pick up a minus sign, which is in front of all three of them. Okay? So an antisymmetric matrix started with 9 independent quantities and ended up with 3. All right. So what's an example of something with 3 indices? Well, one thing I find is sort of thinking like a Rubik's Cube. And that is you're looking at sort of a block or a sugar cube within that. So this sort of cube piece here would be, one sort of data cell inside of this tensor thing. So if we wanted to look at this thing over here on the side, this sort of side cube over here and say, how do I find that? How do I index it? Well, in the same way that we indexed a matrix, that is, I tells me what row I'm in, and J tells me what column I'm in, K then sort of tells you what depth you're in. So this whole thing would be the K1. This next set of 9 pieces here would be the K2. And finally, this back row of 9 pieces would be the K3. So this little cube part here would be go down 2, come over 3, go back 2. Now this visualization isn't unique. There's other ways you can think about it. It doesn't really matter how you visualize it as long as you have some construct in your mind on how to do it. All right. So with that, we're now going to move on, and instead of looking at dot products today, we're going to look at the vector cross product, which is another thing that you often look up in a book. You don't always know where it comes from. Well, today we're going to see how to remember it and how to never have to look it up again. So if you remember, what does the cross product do? The cross product takes 2 input vectors, in this case A and B, and it creates a third vector that is perpendicular to the plane that those 2 vectors sit in, or perpendicular to either one of those 2 vectors. And if you're wondering, geez, I've heard those words before, that was back in Calc 3. So what does it mean that it's perpendicular? What it means is that when you dot your new vector C with either of the old vectors it generated, you're going to get 0. What is A dot B going to give you? I don't know. That's totally arbitrary. It could be a lot of different things. Could give you 0, could give you, not 0. But the point is that when you use that cross product to generate a new vector, that new vector is perpendicular to the vectors before it. All right. And so we're also going to need another new mathematical construct to do the cross product called the totally antisymmetric tensor. So this is epsilon ijk. You will see this in E&M. You might see this as well. So courses like 370, I believe, do this a little bit towards the end, and probably in 410, although I can't say for certain. If you go on to graduate school, you will absolutely see this in your E&M course. You will absolutely see this in your quantum mechanics courses. If you go on to take quantum field theory, you'll see this thing everywhere. If you, basically if you go into theoretical physics, you will see this all the time, and it'll be hard to remember when you didn't know what it meant. So epsilon ijk is a tensor of rank 3. It's not a matrix. It's deeper than that. That's the sort of Rubik's Cube thing we're talking about here. And it has 3 values inside of it. It has 1s, it has 0s, and it has -1s in the same way that our antisymmetric matrix had 0s, positive numbers, and negative numbers. But the antisymmetric tensor only has 0, 1, and -1. And so how do you figure out what this thing is? Well, if it's in order 1, 2, 3, then it's evaluated to be 1. If it's cyclically permutable, meaning that you can take this number off the end and put it in front to get 3, 1, 2, that's said to be a positive cyclic permutation, then that is still a positive 1. Okay. So 1, 2, 3, 3, 1, 2, 2, 3, 1, these are the positive values. If it is -1, that means you're having what's to be a negative cyclic order. Or that if you read through this, that 2 becomes a 1, right? That's no longer in order. That's backwards order. So you're reading this way around, and that's a -1, right? So 1, 2, 3, we're going the wrong way. That's a -1, right? So 1, 2, 3, wrong way, -1. And then if you ever have repeated indices, those are all equal to 0. So what does that mean? Well, if you have epsilon 1, 1, anything really, that's going to be 0. Or epsilon 1, J1, that's going to be 0. As it turns out, most of the elements of the antisymmetric tensor themselves are 0. And so we're going to use this totally antisymmetric tensor to calculate our cross product. So if I have C being produced by the cross product of A cross B, then what does that mean? Well, it means that C is written in terms of some component of it times some unit vector, right? This is just what we had done earlier when we said, hey, A is equal to A sub I, E sub I here. Well, the same idea, we're going to do the same thing now. So we get epsilon ijk, aj, bk. So then, when we explore this a little bit further, we're now going to look at the ci component of this thing, which is right here. So now we're going to get this epsilon ijk, aj, bk, which is a lot of stuff to keep track of, right? You have all these letters now where you didn't used to have them. And so the first thing we need to know is a little bit of language. When we just have a single index by itself, not repeated, we call that a free index, meaning that we can choose it to be whatever we want it to be, but we know that it has one singular value. When we have an index like j or an index like k that's repeated, we know that that means it's a summed index. So we're going to put in a 1, a 2, and a 3, or whatever the dimensionality of our space is to evaluate this thing. And when we sum over that index, it doesn't really matter if we call it j or k. We often just call it our dummy variable summation, which is kind of a funny way to say it, but that's all it is. So the question is this really a cross product? Well, you're going to explore that in some homework coming up. So let's look first at the following. And I want you to sort of pause the video here and think about what is your answer. If I write C1, that means epsilon 1 jk, right? So this is a sum over j and over k. How many terms are we going to get from that sum? Right? And when I say how many terms, I always mean how many non-zero terms. If you were to strictly do the sum without worrying about non-zero terms, you would get 9, right? Because you would get 3 from j and 3 from k. But we know that most of those terms that we get are going to be 0. So how many non-zero terms are we going to get? And hopefully you can fill that in over there. All right. So now I'm going to write out C1. If I write out C1 and I actually do this sum, at least the first sum, over j, right? I get j is 1, and then I add that to the j is 2, and then we add that to the j is 3. And then we look back and go, oh, that's going to be 0, right? Why? Because that's a repeated sum, or a repeated index. That is not 0, at least not yet, because we haven't repeated any indices. So now we'll continue on with this, and let's see what we get. I have the freedom to now do the sum over k. But when I do k equals 1, this term is going to vanish. When I do k equals 2, I'm also going to get what? Nothing from this. I have to go all the way to k equals 3. So then this is equal to epsilon 1, 2, 3, a2, b3. And that's what we get from this term. And now I'll do the sum on this term. Well, in the same way, when I do k equals 1, I'm going to have a repeated index here, so that's going to give me none. When I do the k equals 2, that'll give me something, so great. Epsilon 1, 3, 2, a3, b2. And then when I do the sum, when I put in a 3, well, that's not repeated, so that's going to give me none again. So C1, which looked like a big mess to start with, is actually quite simple. It's just 2 terms. And what are those 2 terms? Well, when I have epsilon 1, 2, 3, we know that's positive 1. So that's A2, B3. Epsilon 1, 3, 2 is anticyclic, or in the wrong order if I read through it, and that becomes minus A3, B2. All right? So what does this mean? This is now your cross product, which you might have seen in a slightly different form before. You might have seen this as CX equals AY BZ minus AZ BY. And then you would look up the other components to it as well. Well, that's great. All of those things are there. All of those things exist, and you can look them up if you want, or you can use your antisymmetric tensor to generate it. All right. So, all right, let's just do C2 as well, just for good measure. C2 is going to be epsilon 2jk, aj, bk, which we will then write out as epsilon 2, 1, 3, a1, b3, plus epsilon 2, 3, 1, a3, b1 equals, this is now a incorrect order, so minus sign, a1, b3, plus a3, b1. Now, if you didn't follow what I did, let's just say it a little bit more carefully here. I'm doing the sum over j. Well, the first term I try is j equals 1. But once I've done that, I know what k has to be if I'm going to get a non-zero result. So I get 2, 1, 3, 1, 3, and then I do epsilon 2. I'm going to put in 3, which means this has to be 1. So there we go. And then I just use the property of cyclic and anticyclic to get the minus 1 and the positive. In your homework, I'm going to ask that you show this is the case. All right. So now we're going to recognize that when I write A cross B, and I want to look at the ith component of that, that's epsilon I, j, k, a, j, b, k. So that's well and good. But what about when I want to check things like since this is vector ci, is a dot c actually equal to 0? Well, let's write it out and find out. So if I do a dot product, what I then get is ai ci, right? That's what that dot product means, which means ai epsilon I j k a j b k. Now in this case here, I don't actually have any free indices like I might have before. So now I get epsilon I j k, ai, aj, and bk. So what does that mean? Well, I now have a sum over these three things, and the question is whether I'm going to get a 0 or non-zero result. I'm going to do this in a rather sophisticated way, and I'm going to hope that you guys are able to follow it. If you're not, please do see me in office hours and ask for help. First thing I'm going to do is I'm going to swap the order of two of these indices in the epsilon tensor. Why? Because I know it's totally antisymmetric. And when I swap the order of those two terms in an antisymmetric thing, I'm going to produce a -1. So we're then going to get minus epsilon j I k a I a j b k. So what happens? I get a -1 because I swapped those two things. That's all I've done. Now, why did I want to do that? Well, if you ever want to show that something that's ugly is actually equal to 0, you almost always accomplish that by showing it equals negative itself, which means that it has to be 0. So I've swapped that order. Now, why did I do that? Well, I did that because I want to introduce the negative sign. Right? That's the part that is non-intuitive, but is sort of obvious at the end. So how do I use that information? Well, the next thing I'm going to do is I'm going to swap the order of these two letters. You might say, what do you mean swap their order? I'm literally going to just write them in the opposite order that they were. So it's just like 3 times 4 is 4 times 3. Okay. So now when you look at that, you might say, okay, well, what did you do? Again, all I did was swap those two things. Well, it turns out that's the magic. That's everything right there. Why is that? Well, now what I have is the first component of the tensor is the first component here. The second component of that is the second component here. And the third component of that is the third component here. In the same way that above, the first component was the first, the second was the second, and the third was the third. So this is now simply A dot C again. Why is that? Well, let me write it one more step. Hopefully that will help. Now I'm going to write this as minus AJ out front, epsilon j I k, ai b k, which is then what? Well, what is that? That's the same thing as C, because that says this component, that component, this one, and that one, or minus AJ, CJ, or minus A dot C. So then we have shown that A dot C is minus A dot C, which means it has to be 0. So there's only really one more thing that we have to figure out how to do, and that is we have to figure out how to do A cross B cross C. Right? And this is one of your homework problems that's already assigned. And so now what we're going to do is we're going to say, what does the ith component of A cross B cross C? Now, just to be clear, this does not equal A cross B cross C. Okay. The cross product is not associative, so we have to be a little bit more careful when we're doing that. All right. So what do we get when we do A cross B cross C? Well, let's write it out. So we get A cross B cross C, and again, we're going to look at the ith component of that. Well, that's going to give us epsilon I j k, aj, And then we're going to have B cross C, the kth component. If you look back at your definition for, what does the ith component look like? You see that this is your free index, these are your summed indices. In the same way here, whereas my I is my free index and my J and my K are my summed indices. So then what do we get? Is epsilon I, J, K, A, J. Now this is going to make a new epsilon tensor, epsilon K, and I can't use the other letters because I've already used them, so I'll make it MN, BM, and CN. All right. Now this is why I stressed early on that, what are these things? These are all just numbers. So I can change their orders at will. There's no derivatives in here. So we're going to do that. We're going to change their order. We're going to make it epsilon I, J, K, epsilon K, M, N. And then we're going to get A, J, B, M, C, N. Which, if you look at this, you might say, okay, great, I can rewrite them, but how did that help me? What did that do? Well, what we now get is something interesting, and that is we see that there's actually a sum between our epsilon tensors, because these k's are repeated, they're summed over. So the first thing we're going to do is rewrite these epsilon tensors so that they have the same position that's being summed. So if you remember, this thing is cyclic, so I can put the k in front and scoot the ij over. So I can rewrite this as epsilon k ij, epsilon k m n, and then you get aj bm cn. All right. So what does this mean? Well, if I just sort of strictly speaking write this piece out, what will I get? I get epsilon k ij, epsilon k mn equals epsilon 1 ij, epsilon 1 mn plus epsilon 2 ij, epsilon 2 mn plus epsilon 3 ij, epsilon 3 mn. And so as you look at this, you are almost certainly not going to have any idea what the right answer is, what's coming up next. But we do know a couple of things. We know that when this is put back into this sum, I, J, M, and N will all at the end of the day be summed over. Well, what else do we know? We know at the end of the day that I can't equal J, because you would get a 0 result, and we know that M can't equal N, and we know that in some cases I is going to equal M, and in some cases J is going to equal N, simply because that's how they're going to appear. So at this point here, it's really hard to see where this problem is going. I'm going to skip to the end, and then I'll talk about sort of why this is the right answer in just a moment. What you actually get is something a little weird. It's delta I, J, M, N minus delta J, and then N, M. So what's happened here is these indices appear in the same order, I and M, and then J and N, so I and M, J and N. And then the indices appear in sort of an opposite order, J and M here. Okay. And it has an accompanying minus sign out front. So what we say is when two totally antisymmetric tensors are contracted with one another, and we perform the sum over K, that it is the following identity. For right now, you're free to just use this identity. I may at some point ask you to prove it or to write it out, but let's just talk roughly again where it comes from. Up here, when we are understanding that I, J, M, and N will all be summed over, we know that sometimes I is going to have to equal M. And we know sometimes J is going to have to equal N. And when that's true in a particular way, you'll get this set of delta functions. And then when I is oppositely ordered than, say, N, that's when you pick up the sort of minus sign out front. So for right now, simply know that this is true. This is an identity that you can use. So when you're doing this back cap, you're going to plug this identity back in, and that's where you're going to see this result pop up. What I wanted to also do is talk about why this notation is so useful. Well, it allows you to save yourself a lot of writing. So for example, in your textbook, you're asked in your homework set, you're asked to calculate the derivative of a cross product. Let me rewrite this just a little bit here. ddt of r cross s. Well, if you were to put in what the cross product components were from some sort of table, right, or some sort of formula lookup, you would then have ddt of, a messy six-termed quantity. But instead, what I'm asking you to do is to calculate ddt of the ith component. And so now we have ddt of r cross s ith component, which we can now put in terms of epsilon ijk. And then we have a product rule of these three quantities, but this is constant, so it comes outside. And now you get something that's actually not too bad. You get the epsilon ijk out front, that derivative times this, plus this times that derivative, and it's much more tractable. And it just makes those problems so much nicer for you, in my opinion. Hopefully you'll enjoy working on them. Please let me know if you have any questions, and thank you very much for watching these videos.